Hi, I'm Ming Chen, and today we will talk about the discrete event simulation problem for presentation 6. So in this presentation, we're gonna provide, first of all, the problem statement, and secondly, we're gonna describe how we use to construct the problem in software and what the software and the problem model in the software look like. And the third one is like how accurate the problem gonna be, and then we're gonna demonstrate how to run the experiments and interpret the experiment. And lastly, we're gonna discuss how to optimize the simulations. So the problem that we have right here is that for a television show, Jack Hall is the host. For the show, Cole who want to win $1 million. For Subdue is the player that have to choose between four answer A, B, C, and D, and only one of those is correct. So because Jill has no idea about this problem and she cannot like she can't even eliminate like any of the choices. So there's one option for you is that to call a friend who is not allowed to tell her the answer but can help her to eliminate one of the choices. So Jill call Ed to which he has been given the answer, and he eliminates one of the answer for her. So there are three options for Jill to choose. The first option is to change her choice. The second one is to not change her choice. And the third one is to make it no difference if they change or not. So here we're gonna use 100,000 integrations of Monte Carlo simulation to prove the result. And that's the problem statement. That is our problem statement.
All right, so what principles did we use to set up and randomize within our code? So in our code, we initially had to randomize the contestant's initial pick by using rand, and it would generate a number between 0 and 1, and depending on where that fell, whether it was less than 0.25, less than 0.5, less than 0.75, or so forth, it would pick a correct answer, either 1, 2, 3, or 4. Then it would also do the same with the contestant's answer, so you could compare if they got it right or not. This worked easy for the first pick and for the first experiment, just seeing how many they'll get right. But when you started to introduce the other option, which is after you pick, the game host would then eliminate another one of the answers, assuming you didn't pick correctly already, and then give you the option to switch to pick one of the remaining two. And in the second experiment, we actually programmed it so you were forced to switch because we wanted to see if it made more sense to just stick with your original answer or to switch after one was eliminated. And that required a large number of if statements the way we did it, just to ensure that MATLAB didn't eliminate the answer that the contestant already picked or accidentally eliminate the right answer. So it took a lot of loops, but it eventually worked. Next, we'll discuss the accuracy of the problem to reality. So the example we thought of was how to be a millionaire. At one point within the contest, after you pick an answer, or actually before you pick, because you can't really lock one in, if you don't know, you can phone a friend. So we're going to operate under the assumption where when you phone a friend, they do not know. And we'll just say that the game host eliminates one, and you now have the option to switch your answer. So you can move from answer 1, let's say they eliminate 2, and you can pick either 3 or 4. So in that scenario, this simulation would represent that, and it shows accurate results. So I'll now get into the actual code for a second. Here is the initial part of the code that will actually pick the right answer and generate it in Z. And then here we're doing it for X. So as you can see, rand will generate a number. Depending on whether it falls within these ranges, it will pick. And same thing down here. And then as you go further down, it's checking to see if the correct answer equals the randomly selected answer. And if it does, it'll tally that up. We run it 100,000 times, and it eventually gives us the output. And then if you keep going down, you'll see where we had to incorporate all the ifs and else ifs. And what these are doing is essentially, after you pick a correct answer, it's going to cross-check and make sure that the answer that it chooses to eliminate isn't that answer that you picked. And if it is, obviously, it tells you got it right. If it's not, then it'll loop through again, just ensuring that it's not eliminating the correct answer. And then after it does that, it also has to make sure it not only it can't eliminate the correctly picked answer, but it also can't eliminate the actual right answer. So that's why it's got to go through like 16 different combinations to ensure that it eliminates a choice that isn't already picked and isn't the right answer. So now I will pass it off to Will, and he'll go over the results.
So basically, if we scroll down to the bottom of the code, you can see that we have an elimination total, a choice total, and then a choice 2 total. Now, what we have, the eliminate was basically just so we could make sure that it was eliminating for every single iteration, and that allowed us just to validate that what we were doing in the code was correct. So we still have that up there. But our original choice percent correct is C over 100,000, because as Reagan mentioned, we did run the code 100,000 times. And this is assuming that you do not change from your original choice. If you do change your choice after one is eliminated, then you'll have choice 2, and that's our R variable, and we will divide that by 100,000, and that will give us our totals at the end of the code. As you can see, we do have a lot of lines of code, around 317, and that's just because this is a pretty brute force method. There are other ways of doing this, but this one makes sense from a brute force standpoint, and that's how we decided to code this one up. So if we go ahead and run, it takes a little bit to run this code because of the 100,000 iterations, but the 100,000 iterations allows us to optimize the solution. So once we get a solution, we can talk about the results. So as you can see, if we keep our original answer, then we'll get around a 25% correct. And then if we change our original choice, then we'll get around a percent correct of around 38%. So generally it is better to change your choice after one is eliminated, and this elimination clearly helps by a lot. The original choice percent correct is around 1/4, which makes sense because if you don't know, it should be around 25%. The change choice is around 38%, which is actually a little bit higher than expected. But this also makes sense because once you eliminate one, then it should be easier to guess than the other 3. So that's how our code works and how it's optimized. And as you can see, it runs a lot like what you would expect to receive from an actual game show in reality. Thanks for listening.